we continue with implicit functions. Now, if z is equal to f of x, y, then we say that we've expressed z explicitly in terms of x and y. And an example is z is equal to 2x squared plus y. Then we can find del z del x, which is 4x, and del z del y, which is equal to 1. But if f of x, y, z is equal to 0, where z is a function of f of x, y, then we say that this is an implicit function. Implicit because in this equation here, we can't just simply make z the subject. Z is part of a function. We can't just simply make z the subject, as we saw in the other examples. So now here, we could be required to differentiate z partially with respect to x, or differentiate z partially with respect to y. And this one here is equal to, is simply fx over fz and fy over fz. This is actually the theory, which could be proved, but I won't bother you with the proof. So if z is expressed implicitly, or your function is an implicit function, then if you are asked to differentiate z or find the partial derivative of z with respect to x, it's the same as differentiating the function partially with respect to x and partially with respect to z. You divide and you negate, right? Let's look at an example. S squared sine y. Let me take it away. S squared sine 2y minus 5z is equal to 1 plus y cos 6sz. We are required to find del z del x and del z del y. Before we start, we must throw everything to the right hand side so that we equate to 0. By doing that, I have s squared sine 2y minus 5z minus 1 minus y cos 6xz is equal to 0. So here we differentiate the function partially with respect to x. And I'm going to get 2x sine 2y minus 5z. 1 is a constant, it goes to 0, and here I get plus y. Okay, what are different cos? I get minus sine, right, which make it plus. So sine 6x z. What are different with respect to x? I get 6z. So I'm going to get 6, the y in front, and z. Okay. Now I find fy. Differentiating the function partially with respect to y. And I'm going to get 2x squared cos 2y minus 5z. When you differentiate cos, sine, we get cos, and we maintain the angle. Enter differentiate here with respect to y, and I'm going to get 2, because this is a constant, and it becomes 4. Okay. Plus, okay, minus, all this is a constant, because it has no y. Differentiating this with respect to y, I'll get 1. So I'm going to get minus cos 6x z. Next, I differentiate the function with respect to z, and I get f that I have minus 5 x squared cos 2y minus 5z plus 6xy sine 6xz. Now, if you don't get the differentiation, you call me and I'll just take you through. At this point, I just hope you are comfortable with partial differentiation. You understand? Okay, so now I go ahead and apply my theory. I can clean the question now. Remember, the theorem says that if a function is written implicitly, like here, even though z is a function of x and y, it is part of the function, okay? So then our del z, del x is just minus fx, fz. So we just divide to get that, right? So del z, del x is simply minus into brackets fx is 2x sine 2y minus 5z plus 6y z, the sine of 6x z, all inside the square bracket. I divide this by fz, which is also mine. Oh, okay. The minus will affect the side, right? So which is also going to be minus 5x squared cos 2y minus 5z plus 6xy sine 6xz. Okay. This is our del z, del x. We can go ahead and find del z, del y, which is also minus fy over fz. And I'll do that one below. So del z, the y, s, we write fy, we negate it. And fy is 2x squared cos 2y minus 5z minus cos 6xz, all in the square brackets, divided by, I can clean this now, fz, and my fz is minus 5x squared cos 2y minus 5z plus 6xy sine 6xz. Good. Now, this is what we call implicit differentiation. Implicit differentiation. Wow. I hope it is clear. So I would stop it here.